Now, in this section, we'll study about work and power and rotational motion. As we already studied about energy in rotational motion, work and power analysis is quite important because just like the case of translational motion, in rotation also in many of cases we apply work energy theorems. Like if we just talk about work, we can say for translational motion, if we are having an object which is pulled with a force F and if it is displaced by the displacement S along the direction of force, we know well that the work is given as Fs, or vectorially if we talk about it can be written as the dot product of force and displacement. And if in a situation force is varying, we can find out work as integration of F dot dx from 0 to S. Now, this is the situation we use when force is a function of x. Similarly, when we talk about rotational motion, where all particles of body which is under rotation revolve in different circles. So, as a special case, if we talk about an object of mass and revolving on a circular path, say the radius of the circle is r, and it is being pulled by a tangential force F. In this equation, we can state if it is tangential and the body is displaced by an angular displacement theta by application of this force, then we can say the turning effect of force, which is the torque acting on the object, can be given as Fr. So in this situation, we can write torque is Fr. And as force is always tangential, so for every elemental displacement, the displacement vector is in the direction of force vector as force is tangential. So we can say work done in displacement by theta is, this work can be written as force into r theta, because along the length of force throughout the motion, the displacement will be r theta. This is the arc length to which the body is displaced. We can write it as Fr theta, and Fr can be written as a torque applied onto it. So this can be written as tau theta. In the similar situation, if say force is acting in some other direction from the angular displacement, we can take the component of force. So vectorially, this can be written as tau dot theta, or more precisely, we should write delta theta, the angular displacement vector for the situation. And if here the force depends on the angle theta, work can also be written as integration of tau d theta from the integration 0 to delta theta, or the angle to which the body is rotated. This is similar to the situation we have studied in case of translational motion for uniform force and the force which varies with displacement. Here we talk about the angular counterpart of force in rotation, that is torque, and rather than displacement we are using angular displacement. In sequence, if we talk about the power, we can simply write power is the rate of doing work. So even in rotational motion, the rate at which the energy will be consumed by the body can be taken as power absorbed by the body or power required in rotational motion. So power we can write simply as dw by dt, and for a given torque, the elemental work can be written as tau theta by dt. This can be written as tau omega, because d theta by dt is the angular speed with which the body is rotating. And we can also go for vector representation of power in terms of torque and angular velocity vectors. So power can be written as tau dot omega. This is the way how we define power. And power can be further classified as average power and instantaneous power for a given situation of rotational motion for a body. Average power can be simply classified as total work done upon total time, and instantaneous power is dW by dt, which we have just now calculated, tau dot omega. So this gives us instantaneous power at any instant when the applied torque is tau and the body is instantaneous angular velocity is omega. Let's have an example here based on the power of an object in rotational motion. Here we are given an electric motor of power P which is connected with a pulley and a string with a mass M is hanging. We are required to find the maximum speed at which the mass can be raised up by using this motor. Obviously, we can state that if mass is going up with the maximum speed, the motor will be running at full power P. In this situation, let's consider the pulley is of radius R. In this situation, if tension the string is T, for uniform motion of this block, if it is going up with the maximum speed, we can write the tension as balancing its weight. So we can say here torque on motor due to weight of block is, we can state in the situation the torque will be mg into r, because the tension acting on pulley will be equals to mg and the radius of pulley we are taking as r, so torque will be mgr. So in this situation the maximum power of motor, if we talk, then it can spend maximum power P. So P can be written as mgr into omega. If omega is the angular speed at which the shaft of motor is rotating, so using this we'll get the angular speed of shaft of motor is P by mgr. So if we find out the maximum speed with which the load is being raised up, it can be written as r omega. So substituting the value of omega will get it as P by mg. That's the answer of this problem. Here you can see we are just using the concept of instantaneous power, which is torque into omega, that we have just now studied in the previous slide. In some cases, if we are required to find the average power, that can be handled just by using change in kinetic energy by the time. So this is a simple example to analyze how the power can be used in case of rotational motion of an object.